In the high desert of New Mexico, where the air tastes of sage and ancient volcanic dust, radio telescope arrays stand like metallic flowers turned toward the heavens. Each dish measures 27 meters across, white steel petals catching electromagnetic whispers from distant corners of the galaxy. The very large array spreads across 13 miles of desert floor. 27 individual telescopes connected by underground cables that merge their signals into a single, impossibly sensitive ear pressed to the cosmos. These dishes rotate with mechanical precision, tracking coordinates calculated by computers that never sleep. Motors hum softly as each telescope follows its assigned targets across the sky, moving with the deliberate grace of cathedral bells marking celestial hours. The tracking systems compensate for Earth's rotation, for the orbital motion around the Sun, for the solar system's drift through the galaxy itself. Each dish maintains its lock on distant radio sources with an accuracy measured in fractions of degrees, following invisible beacons across the vast dark. The instruments detect signals so faint that their combined energy, collected over decades of operation, would not power a single light bulb for 1 second. Radio waves from distant galaxies arrive at Earth carrying less energy than a snowflake landing on desert sand. Yet within this cosmic whisper lies information encoded in patterns of electromagnetic radiation, pulsars marking time with atomic precision, hydrogen clouds singing at 21 centimeters wavelength, the afterglow of creation itself still cooling after nearly 14 billion years of expansion. Each telescope in the array functions as a sophisticated discriminator, separating natural cosmic phenomena from artificial signals. The electronics distinguish between the steady hiss of thermal radiation, the rhythmic pulse of rotating neutron stars, and the chaotic bursts from active galactic nuclei. Computer algorithms analyze millions of frequency channels simultaneously, searching for patterns that indicate deliberate transmission rather than random cosmic noise. The software recognizes the signatures of terrestrial interference, cellular phone towers, airport radar, microwave ovens, and filters them from the cosmic data stream. Scientists who operate these arrays understand that most of what they detect follows predictable patterns established by fundamental physics. Stars emit radio waves as nuclear fusion converts hydrogen to helium in their cores. Planets generate static as they rotate through magnetic fields inherited from their parent stars. Galaxies broadcast the collective murmur of their billion suns mixed with the exotic radiation from supermassive black holes. The universe speaks in frequencies that span the electromagnetic spectrum, from radio waves kilometers long to gamma rays shorter than atomic nuclei. But occasionally, buried in this celestial symphony, a pattern emerges that defies immediate explanation and too regular for randomness, too complex for simple stellar physics, too brief for detailed analysis. These anomalous signals appear in the data like questions written in an unknown language. Most prove to be terrestrial interference or instrumental artifacts. Some remain genuine mysteries, filed in databases with coordinates and timestamps, waiting for additional observations that might reveal their nature. The search continues with mathematical patience that spans decades. Each scan covers a small portion of sky, typically the area occupied by a full moon as seen from Earth. Each frequency represents one possible channel where alien technology might choose to broadcast, selected from the millions of radio frequencies that penetrate Earth's atmosphere without significant absorption. The parameter space grows exponentially when astronomers consider different signal types, continuous waves, pulse transmissions, frequency-modulated beacons, spread spectrum broadcasts, Radio astronomy emerged almost by accident in the 1930s when Bell telephone engineer Karl Jansky investigated static interference affecting transatlantic radio communications. His antenna, built on a New Jersey field to rotate like a merry-go-round, detected radio waves from the center of the Milky Way galaxy. This discovery revealed that space, far from being electromagnetically silent, hums with radiation from cosmic sources beyond human imagination. The universe had been broadcasting its secrets for billions of years, waiting for a species to develop the technology to listen. The irony sits quietly in the New Mexico dawn, where coyotes call across arroyos carved by flash floods that occur perhaps once per decade. Humanity broadcasts its own radio signature into space every moment. Television signals carrying sitcoms and dramas, radar beams sweeping for aircraft, cellular phone conversations bouncing between towers and satellites. Earth's electromagnetic footprint expands at light speed in an ever-growing sphere now encompassing thousands of nearby star systems. Yet this planet remains apparently deaf to any response, isolated in a cosmic ocean that may teem with civilizations or stretch empty between rare islands of consciousness. The telescopes operate continuously, immune to weather and human schedules. Motors and electronics consume power 24 hours per day, maintained by technicians who drive across desert roads to replace failed components and calibrate sensitive receivers. The data streams flow through fiber optic cables to correlation computers that combine signals from individual dishes, creating interferometric maps of radio sources with resolution finer than any optical telescope. Observations continue through New Mexico winters when snow dusts the desert and summer storms paint lightning across purple evening skies. Only took 70 years of radio technology for humans to begin wondering who else might be listening among the stars. Only took another 50 years of systematic searching to realize the question might require centuries to answer definitively. Only took this long for astronomers to understand that the universe keeps its secrets on timescales that humble human impatience, revealing its mysteries to species patient enough to listen through cosmic seasons measured in millions of years. The dishes continue their silent vigil, mechanical monks contemplating frequencies where alien voices might whisper across the dark, in darkened observatories scattered across 6 continents. Astronomers contemplate an equation that attempts to quantify loneliness on a galactic scale, the Drake equation. Formulated in 1961 by radio astronomer Frank Drake, multiplies 7 variables to estimate the number of communicating extraterrestrial civilizations within the Milky Way galaxy. Each factor represents a cosmic filter through which potential life must pass, from the formation rate of suitable stars to the likelihood that intelligence develops technology capable of interstellar communication. The equation begins with stellar birth rates measured by space telescopes that catalogue newborn suns emerging from collapsing molecular clouds. Astronomers estimate that our galaxy produces approximately 7 new stars each year, though this rate has declined significantly since the universe's more violent youth 10 billion years ago. These stellar nurseries glow in infrared wavelengths as dust and gas condense under gravity's patient pull, heating to temperatures that ignite nuclear fusion and illuminate surrounding nebulae with the light of creation itself. The second variable considers what fraction of stars host planetary systems. Before 1995, this number remained pure speculation, but space-based surveys now catalogue thousands of confirmed exoplanets orbiting nearby stars. The Kepler Space Telescope, during its primary mission from 2009 to 2013, monitored 150,000 stars simultaneously, detecting the minute dimming caused when planets cross in front of their parent suns. Statistical analysis of these transit observations suggests that virtually every star in the galaxy hosts at least one planet, with smaller rocky worlds proving surprisingly common in the habitable zones where liquid water might exist on planetary surfaces. But planets alone do not guarantee habitability. The third Drake parameter estimates how many worlds per stellar system occupy orbital distances compatible with liquid water, neither so close that oceans boil away nor so distant that they freeze permanently into ice. This habitable zone, sometimes called the Goldilocks region, shifts outward as stars age and brighten over billions of years. Earth itself may eventually become uninhabitable as the sun's luminosity increases, boiling away the oceans that currently sustain terrestrial life. Venus, once potentially habitable, suffered a runaway greenhouse effect that transformed its surface into a hellscape hot enough to melt lead. The equation's biological parameters venture into deeper uncertainty. What fraction of habitable planets actually develop life? Earth's earliest organisms appeared relatively quickly after the planet's formation, perhaps within a few 100 million years of cooling sufficiently to maintain liquid oceans. This rapid emergence suggests that life might arise readily given suitable conditions, or alternatively, that Earth experienced an extraordinarily lucky combination of circumstances unlikely to be repeated elsewhere. The fossil record provides only one example of biogenesis, making statistical extrapolation impossible. Even more speculative is the fraction of life-bearing worlds that evolve intelligence. Earth's evolutionary history suggests that consciousness represents a rare and perhaps accidental outcome among countless possible paths. For nearly 4 billion years, terrestrial life consisted entirely of single-celled organisms. Multicellular complexity emerged only in the last billion years, and creatures capable of tool use appeared within the most recent few million years. Intelligence might represent an evolutionary luxury rather than an inevitable outcome, useful primarily for species that lack specialized adaptations for their ecological niches. The penultimate factor considers how often intelligent species develop technology capable of interstellar communication. Human civilization has possessed radio transmission capability for barely more than a century, an infinitesimal fraction of Earth's biological history. Many intelligent species might never develop such technology, remaining content with local communication methods or destroying themselves before achieving spacefaring capabilities. Others might develop communication technologies based on physical principles unknown to human science, broadcasting on frequencies or using methods that Earth-based instruments cannot detect. The final variable addresses perhaps the most sobering question: how long do technological civilizations survive? Human history offers little guidance. As our species has possessed powerful technology for less than 2 centuries, nuclear weapons, climate change, artificial intelligence, and biotechnology present existential risks that might terminate most technological species within millennia or centuries of their development. Alternatively, successful civilizations might transcend their biological origins entirely, uploading consciousness into digital substrates or merging with artificial intelligences that operate on timescales incomprehensible to their creators. Drake's original estimates suggested that thousands or millions of communicating civilizations might exist within the Milky Way at any given time. More pessimistic assessments reduce this number to a handful, or even suggest that Earth's technological species might be unique within our galaxy. The uncertainty spans orders of magnitude because several parameters remain essentially unknowable given current scientific understanding. Modern researchers expand the Drake framework to consider additional variables that affect detectability. Civilizations might broadcast deliberately, hoping to contact other species, Or they might minimize their electromagnetic emissions to avoid attracting potentially hostile neighbors. Advanced species might communicate using methods invisible to human technology: quantum entanglement, gravitational wave modulation, or exotic particles that interact weakly with ordinary matter. They might have migrated entirely to digital environments where their thoughts occur at computational speeds that compress millennia of subjective experience into microseconds of real time. The equation's elegance lies not in providing definitive answers, but in organizing human ignorance into quantifiable uncertainties. Each variable represents a research program that could occupy scientists for decades. Astronomers search for biosignatures in exoplanet atmospheres. Astrobiologists study extremophile organisms that survive in environments once considered sterile. And archaeologists examine the rare moments in Earth's history when intelligence emerged from animal cognition. Radio telescopes continue scanning frequencies where alien technologies might choose to broadcast. But the Drake equation suggests they might be listening to cosmic silence broken only by natural phenomena. The galaxy could host millions of civilizations that remain invisible to electromagnetic searches. Or it might contain only one technological species contemplating its solitude among 400 billion stars. The arithmetic of loneliness multiplies uncertainties into mystery, leaving astronomers to pursue their patient search through decades measured against cosmic timescales that render human lifespans nearly instantaneous. Only took 6 decades for scientists to realize that quantifying the probability of alien contact requires estimating unknowable parameters with confidence intervals spanning multiple orders of magnitude. Only took this long to understand that the search for extraterrestrial intelligence constitutes a scientific endeavor where negative results cannot distinguish between genuine absence and insufficient sensitivity. Only took a single equation to transform humanity's cosmic loneliness from poetry into mathematics, though the numbers themselves remain as mysterious as the silence between stars. Beyond the orbit of Neptune, where sunlight weakens to a pale whisper indistinguishable from starlight, 2 spacecraft carry humanity's first deliberate messages to alien civilizations. Voyager 1 and Voyager 2 launched in 1977 to explore the outer planets. Now drift through interstellar space bearing golden records that encode Earth's sounds, images, and mathematical concepts for any intelligence capable of intercepting and deciphering these fragile time capsules. Each golden record measures 12 inches in diameter, fabricated from gold-plated copper that should resist corrosion for billions of years in the vacuum of space. The records spin at 16 2/3 revolutions per minute, the same speed used by human phonographs in the 20th century. Though any alien technology capable of intercepting the spacecraft would presumably possess the computational power to decode the recordings at arbitrary playback speeds. Etched instructions on the record covers explain the playback mechanism using universal physical constants: the hyperfine transition of hydrogen atoms, the binary representation of numbers, the mathematical relationships that govern electromagnetic radiation. The selection process for the golden records involved a small committee led by astronomer Carl Sagan, who faced the impossible task of representing all human culture in approximately 90 minutes of audio and 115 images. They chose musical performances spanning cultures and centuries, a Navajo night chant, Beethoven's Fifth Symphony, a Javanese gamelan ensemble, Louis Armstrong's trumpet, traditional songs from Peru and Georgia and Australia. Each selection represents thousands of years of cultural evolution, compressed into minutes of electromagnetic patterns embossed on metal that will outlast the civilizations that created them. The visual component includes photographs of human anatomy, mathematical diagrams, images of DNA structure, representations of the solar system's planets, and scenes of terrestrial life ranging from microscopic organisms to vast landscapes. One image shows a man and woman standing beside a silhouette of the Voyager spacecraft, providing scale reference for any observers who discover the record floating in the cosmic dark. Another depicts human conception and fetal development, explaining biological reproduction to minds that might experience existence through entirely different mechanisms. The records also contain spoken greetings in 55 languages, from ancient Sumerian to contemporary Mandarin, each offering peaceful intentions to potential alien listeners. These messages assume that extraterrestrial intelligences might comprehend the concept of language itself, that they communicate through structured acoustic or electromagnetic patterns rather than direct neural linkage or quantum mechanical consciousness transfer. The recordings include sounds that define Earth's biosphere, wind through trees, ocean waves breaking on beaches, thunderstorms rolling across prairie landscapes, the calls of whales swimming in abyssal depths. Yet the Golden Records faced nearly insurmountable obstacles in reaching their intended audience. Voyager 1, travelling at 17 kilometers per second relative to the Sun, requires approximately 75,000 years to cross the distance between neighbouring stars. During this interstellar journey, the spacecraft will experience micrometeorite impacts that gradually erode its surface, cosmic radiation that degrades its electronics, and gravitational perturbations that alter its trajectory unpredictably. The probability of any alien civilization intercepting these particular objects approaches zero across the millions of cubic light-years of space through which they will wander. Even if discovered, the Golden Records assume that alien technologies would recognize them as artificial constructs rather than natural debris. The spacecraft themselves serve as stronger evidence of intelligent origin than their cargo, but both Voyagers will cease transmitting within decades as their plutonium power sources decay. They will continue their journeys as silent artifacts, invisible to most detection methods, carrying Earth's messages through a galaxy where radio telescopes might scan millions of stars without noticing two small objects drifting between stellar systems. The Voyager missions exemplify humanity's transition from passive listening to active communication with potential alien civilizations. These spacecraft represent the first human-made objects to enter interstellar space carrying deliberate messages rather than incidental electromagnetic leakage. Their Golden Records constitute a time capsule designed for recipients who might not evolve for millions of years after Earth's biosphere has transformed beyond recognition. Astronomers who supported the Golden Record project understood its symbolic value exceeded its practical likelihood of alien contact. The recordings forced humans to consider what aspects of terrestrial existence might interest or inform extraterrestrial observers. The selection process revealed cultural biases and assumptions about universal communication methods. While attempting to transcend the specific historical moment of the late 20th century to represent something essentially human across cosmic timescales, the spacecraft's current positions can be calculated precisely using orbital mechanics and radio tracking data from their occasional transmissions. Voyager 1 travels toward the constellation Ophiuchus, while Voyager 2 heads towards Sirius. Though neither will approach another star system for tens of thousands of years, their trajectories carry them through regions of space where stellar radiation pressure, magnetic fields from the interstellar medium, and gravitational influences from nearby brown dwarf stars will gradually alter their paths in ways impossible to predict over geological time periods. During their operational lifetimes, both spacecraft transmitted unprecedented images and scientific data from Jupiter, Saturn, Uranus, and Neptune. Their cameras revealed active volcanoes on Io, complex ring systems around Saturn, the tilted magnetic field of Uranus, and nitrogen geysers erupting from Triton's frozen surface. These discoveries expanded human understanding of planetary formation and evolution throughout the solar system, providing context for interpreting observations of exoplanets orbiting distant stars. The Golden Records assumed that alien intelligence would analyze their contents using methods analogous to human archaeological investigation. Any civilization capable of interstellar travel presumably possesses advanced materials science, computational capabilities, and perhaps most importantly, curiosity about other life forms. They might decode the mathematical instructions, extract the audio and visual data, and attempt to reconstruct the cultural context that produced these particular selections from billions of possible alternatives. Yet the records also reflect profound assumptions about the nature of consciousness itself. They presuppose that alien minds experience aesthetic appreciation for music, visual beauty in natural landscapes, and emotional significance in representations of love and friendship. These qualities might be unique to biological evolution on Earth, products of specific neurochemical processes that arose through natural selection operating over hundreds of millions of years. Machine intelligences or quantum consciousness might perceive reality through entirely different categories that make human cultural expressions as incomprehensible as the mating songs of extinct cetaceans. The Voyager spacecraft continue their patient drift through interstellar space, carrying their golden messages past regions where human radio transmissions have not yet penetrated. Their trajectories follow ballistic paths determined by gravitational encounters with the outer planets, modified by tiny forces from solar radiation pressure and the interstellar magnetic field. These influences will scatter the spacecraft across volumes of space larger than entire stellar systems, reducing the probability of discovery to infinitesimal levels while ensuring that Earth's messages survive as long as the galaxy itself maintains its current structure. Only took 2 decades of space exploration for humanity to realize that sending physical messages to alien civilizations requires accepting odds of successful delivery measured in fractions approaching zero. Only took 47 years for these spacecraft to reach interstellar space carrying their golden cargo toward encounters that might occur millions of years after human civilization has evolved beyond recognition. Only took this long to understand that the act of sending these messages matters more than their probability of reception, transforming humanity from cosmic observer to active participant in whatever conversations might span the spaces between stars. Across suburban neighborhoods on every continent, personal computers hum quietly through the night, their processors dedicated not to email or entertainment, but to the systematic analysis of cosmic radio signals. The SETI at Home project, launched in 1999, transforms millions of desktop machines into a distributed supercomputer that searches for patterns in electromagnetic noise recorded by the world's most sensitive radio telescopes. These home computers process data packets downloaded from servers at the University of California, Berkeley, examining narrow frequency bands for the mathematical signatures that might indicate artificial transmission from distant star systems. Each computer receives a small portion of radio telescope observations, typically covering a few kilohertz of spectrum recorded over several minutes of observation time. The data arrives as digital files containing millions of measurements representing the intensity of radio waves at specific frequencies and times. Screensavers display colorful graphs showing the analysis in progress, spectrograms that plot frequency against time, with brightness indicating signal strength. Users watch as their computers search for spikes, drifts, and patterns that stand out from the random static of cosmic background radiation, The distributed computing approach emerged from the recognition that searching for extraterrestrial intelligence requires enormous computational resources to analyze the vast parameter space of possible signals. Radio telescopes generate terabytes of data every day, recording observations across millions of frequency channels with time resolution measured in fractions of seconds. Traditional supercomputers, despite their processing power, cannot examine every possible combination of signal characteristics that might indicate alien technology: continuous waves, pulse transmissions, frequency-modulated beacons, spread-spectrum broadcasts, or exotic modulation schemes unknown to human engineering. Volunteer computers worldwide analyze these data streams using algorithms designed to recognize artificial signals against the chaotic backdrop of natural cosmic phenomena. The software searches for narrow-band continuous waves that might represent alien carrier frequencies, rapidly repeating pulses that could indicate digital transmissions, and signals that drift slowly across the spectrum as their source planets rotate or orbit their parent stars. Each detection algorithm represents a hypothesis about how alien civilizations might choose to communicate across interstellar distances using electromagnetic radiation. The project's success depends on the statistical principle that genuinely artificial signals should appear consistently in multiple observations of the same sky region. While terrestrial interference and instrumental artifacts occur randomly or exhibit patterns characteristic of human technology, radio frequency interference from cellular phones, microwave ovens, airport radar, and satellite communications creates false signals that must be distinguished from potential alien transmissions. The analysis software incorporates sophisticated filtering techniques that recognize these earthly sources and eliminate them from consideration. Participants in SETI at home contribute not only their computational resources, but also their human pattern recognition capabilities. The project's website allows users to examine interesting signals detected by their computers, providing tools for detailed analysis of promising candidates. Experienced volunteers develop expertise in recognizing different types of interference and understanding the subtle characteristics that distinguish natural astronomical phenomena from potentially artificial emissions. This crowdsourced approach to signal analysis leverages the collective intelligence of millions of human observers who examine data with intuitive pattern recognition that supplements automated algorithms. The most famous detection in SETI at home history occurred in 2004 when multiple computers flagged a signal designated SHGB02+14A recorded from a region of sky containing no known stars within several hundred light-years of Earth. The signal appeared as a narrow-band emission at approximately 1420 MHz, near the hydrogen line frequency that many SETI researchers consider a logical choice for interstellar communication. Repeated observations failed to confirm the signal, and subsequent analysis suggested it originated from terrestrial interference or instrumental effects rather than alien technology. This experience illustrates the fundamental challenge facing distributed SETI analysis. Distinguishing between genuine anomalies and the enormous number of false positives generated by sensitive detection algorithms applied to noisy data, the software must balance sensitivity against selectivity, detecting weak alien signals while avoiding overwhelming researchers with spurious candidates that waste time and computational resources. Each parameter adjustment affects this trade-off, potentially allowing real extraterrestrial transmissions to escape notice or burying genuine discoveries beneath avalanches of false alarms. Modern SETI at home evolved beyond simple signal detection to incorporate more sophisticated analysis techniques developed through decades of radio astronomy research. The current algorithms search for Gaussian profiles characteristic of thermal emission from alien industrial processes, population inversions that might indicate artificial masers or lasers operating at radio frequencies, and temporal correlations between signals detected simultaneously at different frequencies. These advanced methods require more computational power per data packet, but offer improved discrimination against natural phenomena that mimic artificial transmissions. The project also examines signals that exhibit characteristics incompatible with known astrophysical processes, but consistent with deliberate alien engineering. These might include perfectly stable carrier frequencies that do not drift due to planetary motion, modulation patterns that encode mathematical sequences like prime numbers or transcendental constants, or polarization characteristics that indicate coherent transmission rather than random cosmic emission. Such signals would represent strong evidence for extraterrestrial technology, assuming they could be confirmed through independent observations and shown to originate from beyond the solar system. Distributed computing participants often develop personal investments in their contributions to the search for alien intelligence. Many users run SETI at home continuously for years or decades, processing thousands of data packets and contributing millions of computational hours to the collective effort. Online forums allow volunteers to discuss interesting signals, share analysis techniques, and speculate about the implications of potential discoveries. This community aspect transforms SETI research from an abstract scientific endeavor into a shared human enterprise that engages millions of people in the systematic exploration of cosmic possibilities. The computational requirements for comprehensive SETI analysis continue to grow as radio telescopes become more sensitive and survey larger volumes of space across broader frequency ranges. Modern instruments like the Square Kilometre Array, currently under construction, will generate data rates exceeding the processing capabilities of any existing computer system. Distributed computing approaches may represent the only feasible method for analyzing these observations in real time, requiring millions of volunteer computers working in parallel to keep pace with the incoming stream of electromagnetic measurements. Yet the distributed search faces an inherent limitation that haunts all SETI research: the assumption that alien civilizations choose to communicate using electromagnetic radiation detectable by human technology. Advanced species might employ quantum entanglement for instantaneous communication across galactic distances, modulate gravitational waves to carry information, or utilize exotic particles that interact weakly with ordinary matter. They might communicate using methods that operate outside the electromagnetic spectrum entirely, rendering them invisible to radio telescopes regardless of their computational analysis sophistication. The volunteers who donate their computational resources to SETI at home participate in humanity's most systematic attempt to answer the profound question of cosmic loneliness. Their computers process signals that travelled for years or centuries at light speed to reach Earth, carrying information about distant star systems and the potential civilizations that might inhabit worlds orbiting those alien suns. Each analyzed data packet represents a tiny sample of the galaxy's electromagnetic environment, searched for the artificial patterns that would transform humanity's understanding of life and intelligence in the universe. Statistical analysis of SETI at home results provides insights into the sensitivity and scope of distributed extraterrestrial intelligence searches. The project has analyzed radio telescope data equivalent to observing millions of nearby star systems for periods ranging from minutes to hours, searching for signals strong enough to be detected across interstellar distances using current technology. This observational parameter space, while vast by human standards, represents a tiny fraction of the possible combinations of transmission frequencies, modulation schemes, signal strengths, and temporal patterns that alien civilizations might employ for interstellar communication. Only took the development of personal computers and global internet connectivity to enable millions of individuals to participate directly in the search for extraterrestrial intelligence from their homes and offices. Only took 25 years of distributed computing to realize that crowdsourced analysis might detect alien signals missed by professional astronomers using traditional supercomputers. Only took this long to demonstrate that the search for cosmic companions requires not only sensitive instruments and sophisticated algorithms, but also the patient dedication of human volunteers willing to contribute their resources to a quest that might require centuries to yield definitive answers. On November 16, 1974, the Arecibo radio telescope in Puerto Rico transmitted humanity's first deliberate interstellar message toward the globular star cluster Messier 13, located 25,000 light-years away in the constellation Hercules. The transmission lasted exactly 2 minutes and 59 seconds, broadcasting 1,679 binary digits at a frequency of 2,380 MHz with a total power of 1 terawatt, briefly making Earth the brightest radio source in the solar system at that specific wavelength. This digital sequence, when arranged in a rectangular grid of 73 rows and 23 columns, forms a pictogram designed to convey basic information about human civilization, terrestrial biology, and our location within the cosmos. The message begins with representations of numbers 1 through 10 encoded in binary notation, establishing a mathematical foundation that any technologically advanced civilization should recognize regardless of their specific counting systems or symbolic conventions. These numerical concepts provide the interpretive key for understanding the more complex information that follows: atomic numbers of essential elements, the double helix structure of DNA, human population figures, and dimensional specifications of the Arecibo telescope itself. The binary encoding assumes that alien recipients would recognize patterns in the electromagnetic transmission and attempt mathematical analysis of the digital sequence. Dr. Frank Drake, who designed the message's content, faced the challenge of representing complex scientific concepts using only ones and zeros arranged in a two-dimensional pattern. The pictogram includes stylized representations of hydrogen, carbon, nitrogen, oxygen, and phosphorus atoms, the fundamental building blocks of terrestrial biochemistry. These atomic diagrams use binary notation to specify the number of protons in each nucleus, providing information about Earth's chemical composition that might allow alien scientists to understand the molecular basis of human life. The DNA section of the message depicts the double helix structure using a simplified diagram that shows the 4 nucleotide bases and their arrangement in genetic code. Adjacent numbers specify the approximate count of nucleotides in human DNA, roughly 3 billion base pairs encoded in binary format. This biological information assumes that alien recipients would recognize DNA as a information storage molecule rather than arbitrary chemical structures, requiring them to possess sophisticated understanding of biochemistry and molecular biology comparable to human scientific knowledge. Human anatomy appears in the message as a stick figure representation showing basic body proportions and bilateral symmetry. Numbers alongside this diagram specify average human height using the wavelength of the transmission itself as a unit of measurement, approximately 14 times the 12.6 centimeter wavelength of the 380 MHz carrier frequency. The message also includes Earth's human population at the time of transmission, approximately 4 billion individuals, though this figure has nearly doubled during the 5 decades since the signal began its journey toward Messier 13. The solar system representation shows 9 circles indicating the planets known in 1974, with Earth displaced slightly toward the stick figure human to identify our home world. This astronomical information locates humanity within a specific stellar system, though the message provides no indication of the Sun's position relative to other stars that might serve as navigational references for potential alien visitors. The diagram assumes that extraterrestrial astronomers would recognize planetary orbital patterns and understand the significance of highlighting Earth's position among the solar system's worlds. The message concludes with a diagram of the Arecibo telescope itself, a parabolic reflector 305 meters in diameter that served as both the transmission antenna and a representation of human technological capabilities. The telescope's dimensions appear in binary notation, using the same wavelength units established earlier in the message, providing alien recipients with information about the scale of human engineering projects and electromagnetic communication systems. This self-referential element suggests that the message originates from a civilization capable of constructing large-scale scientific instruments for astronomical observation and interstellar communication. The target destination, Messier 13, contains approximately 300,000 stars packed into a spherical region roughly 145 light-years across. This globular cluster formed during the early epochs of galactic history, containing ancient stars with low concentrations of heavy elements compared to younger stellar populations like our Sun. The cluster's age, estimated at 11.65 billion years, means that any planets orbiting its member stars would have formed from primordial gas containing relatively few of the carbon, oxygen, and silicon atoms essential for terrestrial-type biochemistry. Globular clusters present both advantages and challenges as targets for interstellar messaging. Their high stellar density increases the probability that multiple star systems might detect the transmission, but the gravitational dynamics of these dense stellar environments make stable planetary orbits difficult to maintain over billions of years. Computer simulations suggest that most planets in globular clusters would be ejected from their parent star systems through gravitational interactions with neighboring stars, leaving few worlds where complex life might evolve and develop technological civilizations. The Arecibo message travels through interstellar space at light speed, currently located approximately 50 light-years from Earth in the direction of Messier 13. The electromagnetic wavefront expands as it propagates, reducing the signal's intensity according to the inverse square law. By the time it reaches its destination, the transmission will be nearly 1 trillion times weaker than when it left the Arecibo antenna. Any alien receiving system would require extraordinary sensitivity to detect this faint signal against the cosmic radio background, suggesting that successful reception might depend on technological capabilities far exceeding current human engineering. The message's binary format assumes that alien civilizations would recognize artificial patterns in electromagnetic transmissions and possess the computational tools necessary to decode digital information. The choice of 1679 as the total number of bits reflects its factorization into 2 prime numbers, 73 and 23 Afra, suggesting that mathematically sophisticated recipients might arrange the sequence into a rectangular grid to reveal the pictographic content. This approach requires alien mathematicians to recognize prime factorization as a key to unlocking the message's meaning. A reasonable assumption given the fundamental role of prime numbers in mathematics across all possible number systems. Radio astronomers who supported the Arecibo transmission understood that the message served primarily symbolic rather than practical communication purposes. The project demonstrated human technological capability to broadcast coherent signals across interstellar distances, while forcing scientists to consider what information might be most valuable for initial contact with alien civilizations. The message selection process revealed assumptions about universal mathematical concepts, biological principles, and technological development that might or might not apply to extraterrestrial intelligence. The transmission also established a precedent for active SETI, the deliberate broadcasting of signals toward potential alien civilizations, rather than passive listening for extraterrestrial transmissions. This approach raises complex questions about humanity's right to announce Earth's presence to unknown alien species who might possess hostile intentions or advanced technologies capable of interstellar travel. Some scientists argue that active messaging represents an unacceptable risk to human survival, while others contend that Earth's electromagnetic leakage already makes our presence detectable to sufficiently advanced alien observers. Contemporary analysis of the Arecibo message reveals both its ambitious scope and inherent limitations. The pictographic approach assumes that alien visual systems would interpret two-dimensional patterns in ways comparable to human perception, that their mathematics would recognize binary notation and prime factorization, and that their scientific understanding would encompass atomic theory, molecular biology, and astronomical observation. These assumptions might prove incorrect for machine intelligences, quantum consciousness, or biological forms that evolved under entirely different physical conditions. Only took 25 millennia for the Arecibo message to complete its journey toward Messier 13, carrying human information at light speed toward ancient stars that formed when the universe was less than a fifth of its current age. Only took 3 minutes of transmission time to broadcast humanity's first deliberate attempt at interstellar communication toward a destination containing hundreds of thousands of potential alien civilizations. Only took this long for scientists to realize that sending coherent messages across galactic distances represents both an act of cosmic optimism and an acknowledgement that meaningful communication between species might require timescales measured in geological epochs rather than human generations.